Okay, hi guys, welcome back. So today we'll be doing the NLP, but one of the latest architectures for NLP. So we're doing transformers, and I think embeddings also part of it. Yeah. So let's start.
Thanks, Chicken. So last week, you should have seen Chicken demonstrate some Hugging Face libraries, including GPT, which is a type of transformer. Then there's also other like sentiment analysis. I also believe using BERTs, right? So all those are also extensions to transformers. So just to give everyone an introduction, the transformer architecture came out in 2017. And since then, it has dominated practically every natural language processing or NLP task. That's why this transformer model has like ousted the decades-old recurrent neural network model and become like the de facto network for NLP. Yeah, however, that's not to say it's perfect. It's just better than what past models could do. Of course, there could be better networks in the future, but today I think it's quite exciting to introduce you this architecture because it has so many practical uses and it is easily usable, especially with libraries such as Hugging Face that give you the pre-trained models. Okay, so before we start, I actually have some fun activities that I would like you to do along with me. Okay, so that we can get an understanding of like how these transformers might actually work. So are you ready? So the first thing, okay, so I don't know if you all played this before. This is called Find Waldo. Okay, so Find Waldo is a game where you need to find this guy over here. You see this guy with the red cap. So on your marks, get set, go. Try to find Waldo in the picture on the right. Okay, and if you are done, just put a thumbs up so I know you're done. We see who can find it faster. So look at this picture there. Can you find the guy with a red hat? I'll give you a while. Okay, this might be tough, right? You find it, you don't have to shout out the answer. You just put a thumbs up so I know that you found Waldo. So nice, Chicken found it. So just wait a while for like one or two more to find. Maybe one more. I just wait for one more. Then I'll tell you the answer. Okay, 10 more seconds, 10 more seconds. Come try your best. Try to find where is Waldo. I'll just
you picked a hard picture.
Have you played this before, Chicken?
No, I played another the books, but this picture that you picked, you selected is quite hard.
Okay, so the winner is Chicken. Okay, so Chicken, you want to tell everyone where the Waldo is? You can like draw on the screen or something.
It's on the right, top right. Yes. Up near the lion, on top of the lion.
So for those who can you see the circle? Yeah, so Waldo is here. This part here. They only show the head. Okay, so must be wondering why I gave this exercise, right? So let's go and look at some of the guiding questions. So if you look at that image over here, okay, what is the issue that you kind of face? Okay, I mean, I gave one of the pointers that is like there's too many information in this picture, right? You need to find where Waldo is. It's very hard to actually know where to actually focus, right? So maybe Chicken, you want to share like how do you try to find Waldo? What are your strategies that you use to do it?
I just like look from left to right, sweep the picture. There isn't much strategy.
So you did something like what CNN did, right? You just look at this patch, you look at another patch. Is it something like that? You look at another patch and so on?
Yeah, something like that.
Something like that, right? Yeah, so I like to leave this here, okay, with you. I will go back to this again later on when we cover like what a transformer is. Okay, but this is one of the key insights, okay, that is used in a transformer. Okay, we will cover that later. So today we have a second activity. Okay, this is I'm gonna keep this more interactive and like lighthearted at the start, so you can actually see how this transformer like tries to do stuff, okay, by doing it yourself. Okay, so you can either grab a paper or a pen, or you can open a text box in your browser, okay, or a text pad. Okay, and basically what I'm about to do is I'm going to give you a sequence of a total of 15 digits. Okay, but I will show you 5 digits at a time. Okay, but you are allowed to only store 5 digits as your memory bank on the piece of paper. Okay, so the aim is to memorize all 15 digits. So we will see whether you can do that. Okay, so I just give you all like maybe half a minute or so. Can you all get ready like a text box or text pad or some paper to write down some numbers?
So this means that you are only allowed to keep 5 digits out of the 15.
I will only display 5 at a time. Then you're allowed to update your memory bank of 5 digits anytime. Yeah, but you're only allowed to store at 5. No cheating. Don't write more than 5. Okay, so Chicken, I think you're ready. How about the rest? Can I get some response?
Okay.
I'm ready.
Ready, all right. Corinne, you are there? Okay, so again, this is a competition to see who can memorize the 15 digits, okay? With only 5 digits as your memory bank. Okay, are you ready? Okay, go. So the first 5 digits are this: 1, 6, 2, 3, 8. Okay, and you're allowed to write them down in your paper or your text pad. Okay, I'm moving on. Next set of digits will be 8, 7, 4, 3, 4. So I'll pause here for about 10 to 15 seconds for you all to decide whether you want to swap some numbers from your memory bank or not. Okay. You're only allowed to store like digits in the memory bank, by the way. Don't store letters, okay? Because letters can contain more information, just digits. Okay, how you want to store it, up to you. Okay, I'm going to move to the third line. Ready? And all right, this is the third line. 2, 4, 9, 3, 0. Can you store these numbers in the... You can swap some of the numbers you want, yeah? Okay, and 5, 4, 3, 2, 1. Done. Okay, so we have everything hidden. Okay, I'm going to invite any of you, if you are confident enough, using like your head and the 5 numbers you record, can you all read out the entire 15 digits? Anyone want to try? How about Teji? Are you able to memorize some of the numbers?
Yeah, I guess so. Yeah.
You want to try? You want to try? We see whether you are accurate.
Yeah. Okay. 1, 6, 2, 3, 8.
Okay, 1, 6, 2, 3, 8.
8, 7, 4, 3, 4.
Okay.
2, 4, 9, 3, 0.
Wow, you actually got everything correct.
Oh.
So, can you tell me how did you do it?
Oh. For first line, coincidentally, 6 and 8 is my birthday.
Oh,
and
okay.
yeah, between the 1, 2, 3, and also 6 and 8, so I can easily memorize.
Ah, I see.
And 8, starting from 8, and for second line, 8, 7, so it's going to down the number, and 8, 7, and try to memorize just 8, 7, 3 or 4, and also down and go up. I try to memorize by line, same image.
I see.
And
So
last line I memorize, not write down to my notepad.
I see. Okay, so can I just summarize? So basically, you memorize the first 2 lines in your head, and the last line in your notepad. So if I were to pass your notepad to maybe Chicken, do you think Chicken can give you the entire 15 digits just from your notepad alone? Like if so, you only wrote down 5 numbers, right? And the 5 numbers is this 5 here, right?
Yes.
Do you think if I pass this to someone else and you just tell them some rules that you use, do you think they can reconstruct the first 2 lines or cannot? Just based on these 5 digits alone, do you think you can reconstruct this? I would say no, right? Because you actually use a separate memory bank for the first 2 lines, which is your own head, right?
Yeah, right.
Yes. So anyway, actually quite impressive. Yeah, if you actually for memory champions, they can actually learn all this because they do by associations and by pictures. So indeed, what you mentioned is some of the techniques that a human mind can use. Okay, but actually the point of this exercise, I would like to say is that if you just give 5 digits to the computer to store it, no matter what sophisticated rules you tell it, the longer your sequence, the harder for it to store all this information. Do you agree with that?
Yeah, it's definitely. So my memory is max for 2 lines.
Correct. But thanks so much for participating. I think this is a problem. Okay, this actually highlights that the human mind can remember quite a lot of things. But if let's say we were to repeat this for like 100 digits, okay, where 20 sets of 5, but your memory buffer is only allowed 5 digits, you can see that slowly this will be a problem, right? There will be a memory overload, which means there's too much information to store within those 5 digits. Okay, so actually this was the point that I was trying to drive at for this exercise. Okay, so let's take a look at the problems with existing networks. So we look at the one on the left right now. So this was 2 weeks ago. Or not, actually not 2 weeks. This is probably a month back. We talk about RNNs. Okay, remember RNNs take in 2 values. One is the previous state input and one is the current state input. And this previous state input HT, okay, actually it's HT minus 1, okay, which is the previous step input, and then XT, which is the current input. This HT minus 1, okay, one of the problems of recurrent neural network is that it must memorize all the previous inputs over here. Okay, because you are not going to give this previous inputs to the network again, right? Your RNN only takes in, okay, the equation for an RNN is like this. HT equals to a function of your current input. Okay, so this is a recap of the RNN lecture, okay? It's a function of the current input and the previous hidden state. Okay, so the exercise that I made y'all do just now, okay, is to simulate a hidden state. Okay, so the 5 digits that I asked you all to do is basically if I have my hidden state with only 5 digits. Okay, my input is going to be 5 digits also. My hidden state is 5 digits, and this one is 5 digits. So you can see that if we were to extrapolate this for even longer sequences, it is very unlikely for your for your hidden state here to capture all the necessary information you need in the earlier inputs. Okay, and indeed there's actually a problem with a lot of the neural network, recurrent neural network models. That's why people invented stuff like the LSTMs or the GRUs, gated recurrent unit, or long short-term memory, to help to select which information to pass through. So you need to kind of filter the information. If not, there will be a bottleneck of basically you can't store all the information. So like last time we tried doing Google Translate before transformers, okay, you will realize that it may not be able to translate very long sentences very well because you might lose some of the meaning. Okay, so this is a problem with RNN. Okay, let's take a look at the right side. Right side is a fully connected network, which is the multi-layer perceptron that we did in the first few weeks. Okay, so this multi-layer perceptron, one of the issues with this is that there's actually a lack of sequential information. Like in the RNN, you know, this is time step 1, time step 2, time step 3. The fully connected model just gives everything at the start. So you won't know this is time step 1, time step 2, because everything is fully connected. There's no like indication to the network. And also one of the key problems is there's no sparsity. So like unlike a convolutional neural network where you actually have filters to like sort of like do some form of patching to like look at different patches. Okay, it's sort of hard to focus, right? Like what we did for the Waldo exercise earlier. You don't have that in the fully connected model. So that is actually an issue. Okay, so both of these networks aren't that great to handle like sequential data. The left is more or less the closest for sequential data because it has the time element built in, but it's not perfect because of the memory bottleneck issue. So what can we do? Okay, any suggestions? How can we solve this bottleneck? Okay, if you can solve this issue, you can probably be a Google researcher already, because this is something that people took years to solve. Let me just share with you what a transformer is. Okay, so a transformer, so a transformer is like this. It's something like a fully connected network. Okay, but you have learnable connections. Okay, so you see these colors here, these are like what you pay attention to. Like maybe green is what you pay attention to most and the rest you forget about it. So you can see that like through the network training, okay, it learns how to, based on similarity with the neighboring nodes, it can select what to focus on, what connections to go. So in some sense, a transformer uses the attention to find out where the connection should be. Okay, and this attention is similar to what we did in the Waldo exercise earlier. You need to like focus on what is the important things at a time. You cannot focus on the whole picture. You must focus on like different chunks so that you can actually process that part well. So similarly, transformers, they learn this connection via attention. And this attention is based on similarity in the embedding space. I will cover more on like what does this similarity in embedding space mean. Okay, and the key thing that I want to highlight for transformer is that for transformers, all information can potentially, all information can potentially pass through this network. So what does this mean? Okay, this means that, remember in the earlier RNN, I only depend on this vector here, this earlier state vector. But for transformer, all potential information can actually pass through the network together, okay? And this means that you can actually not have like an issue with the memory buffer. Okay, you can actually process all the information together. So that is actually one big advantage of a transformer model. It overcomes the bottleneck issue. Okay, but you realize something, right? If we do all the inputs at once like this, this kind of looks like a fully connected network. Can you see that this kind of looks like this? Yeah, and the problem with a fully connected network is that there's no sequential information. So how did the transformer architecture bring in the sequential information? And that is actually a very ingenious method of using positional embeddings, which means that instead of just having only the input itself, I also give the input some idea of what the position of the word is. So I can tell this input, okay, you are the first word, you are the second word, you are the third word, by putting in some vector space, okay, some of these words over there. I mean, basically I encode this 1, 2, 3 as an add-on to your existing input. Okay, now it might seem very vague, okay, but we will cover this later on in the next few slides. Okay, I pause here for any questions if you want to ask. Okay, this is an overview slide that I created to like highlight what a transformer is. And if you all have any questions now, feel free to ask. Okay, if not, you can ask me anytime during the presentation as well. Okay, so right now I'll just like to just show you how a transformer could like potentially like be used. Of course, Chicken showed you some examples, but let me just show you a commercial example. It's called AI Dungeon. Let me just do a quick like 1 to 2 minute showcase of this. I didn't create this, by the way, but I thought it was quite cool. So can you see my screen now? The AI Dungeon. So AI Dungeon is a game whereby like you basically they basically train a transformer on some fantasy novels. Okay, and then like for input, they input some of the, okay, let's, oh, wait, what did I do? Okay, you want to choose which one you want? Now we just go with number 4, apocalyptic. Okay, which one? Survivor, soldier. So basically when you select all these characters, they do have some background text that they feed the model with that will help it to generate some text later on. So let me just pick one for you. Okay, I think we can pick like survivor, right? Okay. Enter your character's name. Maybe you can call it Gao Gao. So this is an interactive like text-based game thing where you can actually, like, you are Gao Gao, a survivor trying to survive in a post-apocalyptic world. You have a backpack and a canteen. You haven't eaten in 2 days, searching for food, enter a rundown building, see a wounded man with a huge wound on his back, bleeding out on the floor. No other people in the building, not much food. Okay, what will you do? Okay, so anyone want to give me a sentence? You can key in any sentence here. use your imagination. You can how do you want to save the man or not? The wounded man. Okay, let me just give the first line. Chicken, you want to give a line? Yeah.
Okay, hold on, I'm typing.
You take out your man. Take out, right? Take out
Yeah,
your.
sorry, take out, yes.
Yeah, so let's see what story is generated. So you see, they based on the medical kit, they generate some text. You find a piece of sterile bandage. This grammar error. Okay, piece of sterile bandage. Yes, and tourniquet. Okay, yeah. Okay, so next section. Okay, anyone want to give the next section?
Why don't Hideyoshi-san give the next text? It doesn't have to be complicated. It just has to be some sentence, any sentence. It's okay.
Such a nuisance. More sewing.
Sorry.
Just a moment.
Type something out. Type it in the box.
Yeah.
Don't worry. Yeah.
Yeah, anything is okay.
Yeah, even if it doesn't make sense, we can see how the model interprets it. Yeah.
We can.
So actually, this model was open source for a while, but then the creators decided to train it on even more text, and then they started a company. So now this becomes a proprietary property. You can even download this AI dungeon on your mobile phone.
What is the purpose of this one? Like, is it to generate stories, or is it
So the author, creator of this wanted a Dungeon and Dragons storyteller. So he thought, since transformers are so powerful, why not automate it?
And this, I guess, is GPT, one of the GPTs.
Yeah, right. This is a transformer model. I think this
Can close.
this is a GPT. Yes. So basically, after you give the output, you give it that as an input again and generate the text. Okay. We can make close our wound. Is it?
We can close the wound.
We can close the wound.
Close the wound
of the man.
of the man.
Just put we can close the wound to stop and see what they generate. Not bad. I mean, they figure out that it's from the man. Yeah. That's how in pain, it won't stop the breathing, but you are safe from the man's dying. So it's not very nice, not very good, right? You are alive. Why is it you are alive? Actually, it should be the man's alive. But you can see that there's some issues with this model, but overall, the text is coherent. Thank you. Okay, then let me just give you the next line. Okay, like you see a zombie kill the man. And we see whether it generates plausible text. So yeah,
do you know what is the model based off?
Yeah, I think it's on the site itself.
Oh, okay.
Let me just go and see whether I can find it. Hold on. Is it settings? I remember I read it before. Okay, but I can't really remember. I do know it's based on a model of transformer. GPT-3 text generator. Yeah. So yeah, you can see that.
Yeah.
You can see that actually, like, GPT-3 takes on the biases of the data. It's not perfect, okay, but it basically gets what you input the training distribution in. So that's why a lot of the GPT models, when they train on text, they take out any word that includes the word sex, because if not, you might get those kind of other stories that may not be suitable. So this is, you can read more about AI Dungeon. Is a GPT-3 basically. Okay, I won't delve too much into it because Our aim is not to sell AI Dungeon. Our aim is to talk about transformers. And I just want to get you excited about the potential use cases for this.
Just a side question. Because of the kind of controversy that you just brought up, right? Are there, when somebody creates a model like GPT or do they test the model, or is it open to testing by the public, or is there
GPT-3
in-house?
was not released to the public.
Yeah.
So but I don't think they have released GPT-2. Yeah, and I think Hugging Face implemented GPT-3.
Two. I think it's only for 2.
They have 3 also, I think.
Oh, is it? Okay.
Yeah, basically they re-implemented OpenAI's GPT-3. Yeah, so normally this is not really tested before it's released. Okay, because I don't think it's really used for a lot of things right now. Like this kind of storytelling fantasy is one of the genres because open-ended, you don't have to be perfect. Okay, but if you want to use it to generate legal documents, generate code, you can look out. Okay, maybe the next one. We do have text generator, and DeepMind tried to use it to solve competitive programming problems. AlphaCode. It's not perfect. You can see it yourself. I won't be going through today for this one, but basically there's things that people have tried out. But if you want to use it for more commercial applications where accuracy is important, then you wouldn't want to use GPT-3 because there's no safeguard. Yeah, it will just generate based on statistics, and you don't know whether your text that is generated is it controversial or not. But if you want to generate stuff for leisure, create a novel, or in fact, people have used GPT-3 to create their own fake blog posts. Okay, so you can type in a certain sentence, and then the whole blog will be generated out for you. And in fact, one of the young teenagers did that, and his blog got one of the top few blogs. And then at the end of it, he mentioned that, oh, hi guys, actually it was all faked. It was all from GPT-3. I was just testing it out. So if you want to generate plausible stories, plausible text, GPT-3 is definitely okay. But if you want to generate factually accurate stuff, then that's not the use case for it. Yeah, I hope that answered the question. Yeah. Chicken, you okay?
Yeah, thanks.
All right, so let's move on. So I hope you all are interested to find out more about how this works. Okay, so let me step you through the process of how a transformer model works. Okay, first up, the world's information is for example, in words. Okay, it's not very computer friendly. All of you all here are programmers. The computer takes in numbers, okay, or takes in computer instructions and compute stuff, and they are very good at computing numbers. But computers cannot process words directly. We need to make it into a form suitable for the computers to process. And for deep learning, this form means that it cannot be words, it must be numbers, because you can only do back propagation on numbers. Makes sense because it's a differentiation operation. So how do we do it? Okay, so there are a few ways to do it for how to convert words into different chunks so that we can fit in these chunks into the computer. So remember for RNN, I gave you all the notebook, which is a character-based RNN generator to generate Shakespeare text. So it generates the text based on the character level encoding, where you encode different characters like L, E, A, like learning, L, capital L, E, A, R, N, I, N, G, and so on. You can even make all of them to be uncased, means lowercase, or you can make remove full stop, remove space. Basically, you can do stemming also. There are various techniques to actually reduce the amount of information that you give it, like learning can become learn, but you will lose some meaning. Okay, so character base is basically you take all the characters one by one, these letters one by one, L, E, A, R, N. Of course, the more macro concept will be if you take the word totally, like learning, learn, deep learning. Okay, then there's an in-between also. Okay, why is there an in-between? Okay, firstly, character base is actually great for the number of tokens because there's very few tokens, very easy to encode into the computer. You won't have this problem of exponential growth. Okay, words on the other hand, because there can be so many words possible. Okay, if you were to include the entire list of words as your tokens, you will need a huge training set in order for the computer to know what to do for each word. Okay, that's why there's techniques like stemming, there's techniques like lowercase, that kind of thing to try to reduce the number of tokens. Over here, token is one group of words. Okay, so there's a a middle ground, which is used a lot in like GPT-3, but it's called subword tokenization. And oops, sorry. Subword tokenization basically means that instead of doing words, I just take the most common word, like learn, and then I do a hex ing for like the prefix or suffix. So you realize that this ing appears for a lot of words. So they typically use techniques like called byte pair encoding, where based on probability, they try to group together which are the most common subwords. Okay, and this is a statistical process that you can generate the most common subwords. Basically, you can split the words into different parts so that instead of learning like, okay, let me give you the power of subwords. Okay, let's say you have the word called learning, playing, studying. Okay, and then we have learn, play, study. If you were to do all this as words, right, you will realize that you will need 6 words to do it. Okay, but if you want to do this in subwords, okay, how many words do you need? You just need learn, play, study, and then you just need an extension ing. So you just need 4 words. So you can see that actually there's an exponential decrease if you were to use subwords. I hope from this example it's quite clear. Okay, of course the prefix can also be at the normally the prefix is, if let's say there's these 2 words is combined together, so it's like hex means that it's linked to the front words. So actually in this image that we obtained from this, I obtained from this free code camp, is actually a little wrong. Okay, like learn ed, right, it's not split into 2 words like that. It's actually learn hex ed, because you need to give the word the information that is actually linked to the first part. So this is the idea behind the subword encoding. So same for deep learning, you can actually do you should actually do a hex here also. Okay, so this is the idea behind subwords. The idea of doing this kind of tokenization at various levels is so that you can actually extract out the semantic meaning behind that token and be able to use it in different contexts. So if I know, like, let's say the best way to get the meaning is actually through the words itself. So if I know that there's this word learning, okay, that is very similar to studying, then the next time the model encounters study, it can actually use the stuff that it took in learn, and it can interchange the words. It can find the context better through this semantic meaning. Okay, and that's why also like character-based models are not very good for text, because character, what does a character convey? What does an A convey? What does an E convey? It all depends on the words that is used in, right? The character itself has not much meaning. So a character-based token is kind of difficult to actually learn from. Most people would prefer word-based. I tell you, if we have enough compute, everyone will want to do word-based encoding, word-based tokenization. It's because there's too many words. That's why subword tokenization was invented. So yeah, I think I went into like a little too much detail, but I just want to say that there's various ways of tokenizing your words to extract meaning from them. Okay. So after you tokenize it, how will you encode it into numbers? So the most typical form of encoding used is called one-hot encoding. So for instance, let me give you this example, like I, he, she like machine learning, and end of sentence. And let's say your sentence is I like machine learning, end of sentence. When you encode it into a one-hot encoding vector, what will happen is that, okay, you will, actually this is not really embedding, this is like the encoding. So it's like I will be encoded to like the 1 is over here, 1 0 0 0 0 0 0. Like will be encoded here as a 1 1. That's why it's called one-hot encoding, because in every row there's only 1 1. Okay, so it will be encoded as a 1 2 3 4 5 6 7 7-dimensional vector. Okay, and this 7-dimensional one-hot encoding vector will then be used, okay, to do embedding. Okay, so what's embedding? Let me show you the next slide. So embedding space is like that. So after you do a like one-hot encoding, you can then map each of these words into like a certain embedding space, which people hope, okay, like let's say you have this embedding space is 1 2 3 4 5 6 7. We have 7 dimensions in this embedding space. People hope that each dimension represents a certain attribute. Like maybe the first dimension is like whether or not the scale it is a living being, the scale it is feline, the scale is human, gender, royalty, verb, and plural. So like it's maybe a scale of like how how similar they are in these attributes. Okay, of course, we don't define this earlier. This is actually learned by the model through backpropagation. These categories are just like people hope that they generalize in some aspect. Like each dimension is one orthogonal aspect or one independent aspect of the word. Like whether this is male or female in that dimension, or whether is it living or not living. So this is an example like cat. You can see that it's more towards the living side. Houses is not living, so it's like minus 0.8. Like same thing for like man, woman, queen, king, queen, all are living. Okay, but for gender, you can see that man is like 0.9, king is 0.8, while woman is like minus 0.7, queen is minus 0.9. Yeah, of course, this one is like artificially generated. So how do we view this embedding? Usually we use a form of dimension reduction technique. You can use like TSNE to try to view it in 2D. Or you can use other techniques such as PCA or SVM, PCA or SVD. So these are dimensional reduction techniques that you can use it to visualize. Okay, we only use it because there's no way for a human to visualize anything more than 3D. So, we try to map it down to 2D so that we can see it. So one good thing about like word embedding spaces is that you can see like things that are similar should ideally be grouped in the same, like cat and kitten should be grouped together. Houses should be somewhere far away, dogs should be somewhere far near. It should be nearer the cat and kitten, but it should be further away from house because like it's less linked to that. So with the word embeddings, you can actually extract more information from these words. And next time you encounter similar words, you will know how to handle it. Okay. And one cool thing about word embeddings is that people have also shown that if you train it well, okay, like for example, man is to woman, it can do analogies like this. Man is to woman is to king is to queen. You realize that this vector is approximately the same magnitude. So if you train your word embeddings well, okay, using backpropagation on a suitable large enough text, you should be able to let the model extract the right embedding space to encode each word so that you can do like vector operations on it to preserve the meaning. So like if you take, for example, woman, so people have shown this also, like they take woman minus man plus king, right? A woman minus man plus king, okay, we get queen. Yeah, so you can do stuff like that in the embedding space, which is pretty cool if you ask me. Okay, so I pause here on this slide because actually, if you ask me, the key behind NLP is not so much the transformer model, but the key behind the the key behind NLP is actually word embeddings. If you get the correct word embedding, you will literally be able to generalize to a lot more situations. Okay, I'll move on. So now I give you the overall view of the transformer architecture. So most of this are actually taken from the site called Illustrated Transformer. So you can actually look it there. Okay, so let me just give you the overall view. So the original transformer is like this. You take in a certain inputs over here. Okay, add in some positional encoding. Then you feed it through some layers of multi-headed attention. Okay, this is the encoder stack. So this is called the encoder stack. And then after that, at the other side, we have the decoder. So the decoder would similarly take in like, okay, this is like, for example, if you want to do like stuff like translation. So you take in the outputs. Over here, they put shifted right. Okay, so that the model cannot actually look ahead at the, like it cannot basically look at the next word in order to, so you see you have the output probabilities here. So you basically don't want the model to get the model answer. So you shift it right so that the model can only see things until that current time step. Okay, so the output embedding, okay, this one might look a bit confusing, but let me just give you an example. Like for example, the input could be like I want, and the output will then be shifted right, means once. Yeah, so no, sorry, wrong. Let me just erase. Okay, so let's say the input is I want. You want to predict the next sentence, right? Like I want to. So over here, your output here should be I think it's something like that. I right? Yeah, this should be the okay, let me think about this. I do know that what it means is that it cannot view the model answer, because like given the input is supposed to predict out what is the potential answer. So yeah. Okay, let me go and think about this again. Suddenly I forgot how to explain this part. But the idea behind this shifted right is so that the model doesn't learn from the model answer. Okay, but the idea behind transformers is like this. It goes through another positional embedding here. Okay, and then goes through a few layers again of the multi-header attention. Okay, before it goes through a softmax layer for the output probabilities. So that's the rough idea of the default transformer, whereby you actually use this architecture to try to predict the next word in the text. Okay, so we'll go through more on what this multi-header attention is. So the overview behind the multi-header attention is given here. Basically, they use this thing called query, key, and value. And then based on how similar the query and keys are, you pay more attention to them, and then you multiply them by the value. So this is the equation given here. Okay, so we will cover this more in the next few slides. Okay, so if you are interested, the paper is here. Attention is all you need. Okay. So yeah. So this part on the output shifted right, I'll get back to you all again. Okay, I suddenly forgot how to explain this, but the idea is that we don't basically give the next word answer to the model. Okay, so let's do the overall architecture. So the overall architecture is like this. Okay, like for example, this: I am a student, and then over here the input will be like this. Like for example, a French to English decoder, encoder-decoder. So the input is like this. I don't know how to pronounce this, and the output is like I am a student. So this is the overall encoder-decoder architecture. Okay, so this block is actually repeated many times. You can see this NX over here stands for n times. Okay, it just means n times of this block. This block is repeated n times, n encoder blocks and n decoder blocks, like that. Okay, so what is inside the structure of the encoder block? First, we have a self-attention module, followed by a feed-forward neural network. So the self-attention module is this one, and the feed-forward is down here. So the self-attention and the feed-forward block will then be passed, the output will then be passed to the decoder block, which also has a self-attention, and we have this encoder-decoder attention. So let me just show you what's this. Self-attention. This is the self-attention because it only takes from the output. And then we have the encoder-decoder attention here because it takes from the encoder and from the decoder. And then lastly, it has the feed-forward over here. So this is the block for the decoder attention. Okay, so now I move on to something important. So this is how the self-attention block is computed. Okay, so for example, we have the following in word embedding space. JS use an attendant. Okay, I think I pronounced it wrongly. Sorry for that. so let's say we have a 4-dimensional vector for each of these words here. And this 4-dimensional vector will then be passed through in self-attention, okay, in order to get you this vector here. Okay, let me just illustrate why this self-attention is important. Okay, so earlier on you saw the word embedding space, right? Like for example, cat, dog, cats and kittens are together, dogs a little further, you know, that kind of thing. In the semantic space, it turns out that words don't only have one position in the semantic space. Okay, I think I kind of blown your mind here, right? Each word may not have the same position in the semantic space. Okay, so give you an example. The word bill. What do you think the word bill is? A word bill could be a legislation. The word bill could be a big, you know, the bird's bill. A word bill could be like the food the bill, as in the receipt of the restaurant. So there could be many meanings of the word bill. And how do you know which meaning do you take? Okay, so the answer is actually you have to know the context of where the word is used in. So you need to know what's before what's after, maybe a few paragraphs behind or a few sentences behind. Usually it's 1 or 2 sentences behind and after. Okay, so from the neighboring words, you should be able to figure out what is the current meaning of this word. And that is why this self-attention architecture is so useful, because it allows you to take in the meaning of this word, this word, this word, okay, and then do some form of like attention in order to see like what should my meaning of the word be. Should I take in some of this meanings here and put inside this word? So it allows us to shift the embedding space a bit to take into account those neighboring words. And so like maybe bill, at first it might be original embedding space might be more like legislation, but if we take into account like, oh, the bill was very expensive, then like with the word expensive, it might slowly shift this meaning to receipt. If you get what I mean, it's a slow shift of embedding space. Like for example, the embedding space was initially here, like bill was initially here. And then maybe the word receipt is here. Okay, I'm just going to write the word receipt here. So with self-attention, based on the meaning of like the surrounding words, it could slowly help to shift the meaning here. Can you all see that? Can you all see that the meaning of a word actually depends on the surrounding words? And the self-attention block allows the embedding space to be shifted from one to another, okay, using the surrounding words. And that is actually a key insight behind why transformer methods work so well. It is really the multi-headed attention, or rather the attention module itself is really the, I would say the MVP, if you all know, the most valued player is really the attention block in the transformer module. Okay, it solves, or rather it tries to solve this problem called polysemy. Okay, polysemy means that one word can have multiple meanings. And so how do you know what context this word is? You really have to use the neighboring words. Okay, I spent quite a bit of time on this slide because I think this is important. Y'all have any questions so far for this?
Can I ask how let's say that the first word affects the second word, how does the second attention node know to go back and check where does this word lie in the embedding space for this context? Like how does it know to shift or not to shift?
Okay, so you're saying whether or not the second word should preserve its vector or should shift vector, right?
Yes.
Yeah, so when you evaluate this embedding space here, each of this is done like, you basically don't change the input vector, is it? So each of this is actually done separately. So you can just treat it as your first word, you do it one time, then you do another operation for your second word and so on. So the second word here, okay, the attention vector after you do that second word will also take into the account the original 3 vectors here. So in some sense, you don't actually shift the meaning of the word. You only shift it individually after you go through the self-attention block. And so each of these words will already know what its neighbor's original embedding space is. And then they shift it according to what the original embedding space is to form an updated embedding space. Yeah, so there's no issue of whether to shift or not to shift for the next word because the inputs are fixed. It's only the next intermediate layer, this embedding layer here, that will be changed based on the first layer.
And I assume that this one block is one node in the deep neural net, or is it several layers? Is this self-attention one layer and then the intermediate one layer and then the feed forward one layer? How does this architecture relate to the bigger, the original multi-layer perceptron?
Okay, so in the original multi-layer perceptron, this is the same as the multi-layer perceptron. Sure. It's just a feed-forward block. But over here in this self-attention block, it's like what I drew earlier. Instead of having fully connected connections, these connections are instead weighted to a sum of 1. So like over here, like this node can be like 0.1, 0.3, and then 0.6. So in some sense, we are telling the model that, you are allowed to only sum to 1. Choose your buddies wisely. I only give you like 10 credits. You spread your 10 credits among like 4 people or 3 people. So you maybe give one person 1 credit, another one 3 credits, another one 6 credit. So it is different in the sense that there's a constraint placed on the neural network, whereby you already tell it that, you have to give differing attention to your inputs. So rather than a fully connected network where, you can just give any weight you want. In a self-attention block, your weights, the sum of your weights will be limited to 1. So that is the beauty of self-attention. You force the model to choose what to prioritize. Yeah, people have related self-attention to like neural architecture search, where you search through the possible connection spaces. Okay, but that is, to be fair, that's not exactly true, because you are constrained in the amount of weights you can give to each of the connections. Unlike a traditional neural architecture search, where maybe you can give like weight 1 to all these 3 weights. You can't do that in a self-attention. You have to give like maybe 0.33, 0.33, 0.33. So there's some difference, but the similarity is that you can use self-attention to like choose your architecture, to choose your connections.
So would you say that this is fixed? This is a fixed structure, right? Could you do one more after this before it goes to the softmax layer, or is this you only must have one of this? Like for example, convolutional neural net, you can have many pooling layers and many those what's that padding. I mean, you can choose how many you want, but for this it seems like you only want one of this. Then you go to then you feed the encoder output into a neural net, standard neural net, or is it straight to, yeah?
So strictly speaking, okay, if you only have one block, the transformer module doesn't work very well. You need to actually repeat this multiple times. And that could be due to the fact that maybe to get from build to receipt, you cannot just do it in one fell swoop. Okay, maybe the other meanings need to be updated first. Then maybe it gets to this area. Then when the other words get their meanings updated, then your next self-attention block can bring it here. So it is the case that you might need iterative process in order to get it to the final embedding space that you want it to be. Okay, and that's why over here is n times. Yeah, and there's some subtleties in that. Of course, not all the times you do in the n times are useful. Sometimes it's not useful. Okay, and that's also where I also will touch on this, like this thing called skip connection, where basically if your multi-header attention here is not useful, you can skip it. Yeah, so this is used in this model architecture called ResNet, residual networks. Okay, I didn't cover this with you all, but the idea is that you give the same block multiple times, and then if the block is no longer useful in helping you process the information, you give a skip connection, at least a path for the gradients to flow whereby it doesn't go through that particular block. Yeah, so this allows us to stack multiple layers together without much loss in performance. So this self-attention block, repeated many times, coupled with this residual connections, is really the beauty behind the transformer.
I've also seen that, so sorry, one more question. Yeah, I've also seen that you can do just encoder without the decoder for certain problems. How and why does that work?
Take for example, sentiment analysis. You don't really need to decode, right? You can just encode into some vector space. Okay, and then you can output like a 0 to 1 vector here. There's no like output to go to. Yeah, so that is why it's not really necessary. Yeah, actually, I think the reason like why there's this encoder-decoder is really for this problem called neural machine translation, where you basically want to translate from like one language to another language. So you give as input one language and the output the other language. So okay, now I can explain this shifted right. I remember it now already. So for example, this is your entire French sentence as your input. Your output will be like, for example, you output one word at a time, right? So your output can be like, I am a student. So your output may be I, okay? And then like over here, the softmax output probabilities here will be for your next word. So like maybe your next word will be M. Yeah. So then you can then take this M and bring it back here. So you can get I, M, then you predict the next word. Yeah. So this is what it means by like shifted right. So if you were to like basically do some prediction behind like whether or not this is predicted correctly, you can then use your original sentence, like M, you can compare with this. Yeah, but you basically don't give the answer too early. You don't give the M over here when you're predicting M. If not, the model might learn to just predict M directly from the input. So that's why the output here is shifted right. It shifts right so that the current word they are predicting is not given as an input. Yeah, so yeah, I remember this architecture now. Yeah. Okay. Yeah, sorry, that was a digression, but yeah. Any questions? Any other questions for this?
Yeah, I think one of the comments is that in this case, the word Bill doesn't have a precise position in the vector space.
Yeah. In the n-dimensional graph, the word Bill doesn't have the precise position in that dimension graph.
Yeah, right. You're right. But usually when people do backpropagation for all this, it will end up being the average of all the possible contexts that it can be in, because you do backpropagation across multiple samples, and then each time you do backpropagation, your embedding space might be different for the word Bill in different contexts. So you might end up with like an average in the center.
Oh, I see.
Yeah, so that's why without this self-attention block, before transformers came into popularity, there's this thing called word2vec, okay, whereby they just basically take in the neighboring words. Similar idea, take in neighboring, also by Google, take in neighboring words and then try to predict the like vector space based on the neighbor words. Okay, but this word2vec had one downside, major downside, which is that it could not adapt this vector, okay, for different words. So normally when people use like word2vec embedding space, they don't really have this like self-attention step in the past. They just basically take in this embedding space where basically like it will like average out across all contexts, right? So this idea for like bill, okay, instead of having a bill like that is defined for like receipt or what, it will just be like average across all the different embedding spaces that could be that could have taken. So you might get this, which is actually not that ideal, because like you don't want your embedding space to not be like the current context embedding space. So without this like self-attention method to like refine the embedding space, it is very difficult for you to just use a pre-trained vector like this and then expect it to work for all situations. Yeah. So again, this is the idea of polysemy, where you want to let the embeddings learn by themselves. Okay, but that's it. I think, okay, I've not done it, but I think it's possible to use the word2vec embedding and put it into the transformer architecture and have it to learn it like that. Yeah, I think it's possible, because a transformer architecture will iteratively update the embedding space. I think it might be possible to do that. But usually when people do the embedding over here right now, you can ask Chicken, but actually release the word embeddings that they use when they actually train it. So people use actually the BERT tokenization and the BERT embedding space embeddings. So there's no need to go back to word2vec. Anyway, word2vec was trained with an inferior architecture. Okay, but the idea of iteratively updating this embedding space to make it more accurate is the key functionality behind the transformer, if you ask me. Okay, I hope that answers the question. Okay, I'm so sorry. I actually think I may not be able to finish this in this session, but Chicken, do we have time for another session to cover the rest?
Yeah, for sure. As in, like, as long as you are okay to continue doing lectures, I think that we appreciate if you take more time to answer some of the questions. I think it will be better for the understanding, because this architecture it seems a bit distant from the multi-layer perceptron. Like he had added so many things into it that it requires explanation for everything that you add.
Yeah,
Because
correct,
it's
correct.
very it's not so obvious what it's doing.
Correct. Maybe
yeah.
I cover one more slide, then I cover the rest for the next time.
Okay, sure, no problem.
Okay, so let me just finish the encoder module. So of course, there's this last part where is the feed forward. So usually in the feed forward, you know, a neural network is basically this function, fx, y equals to fx, where you take in the input x and then you output to y. Okay, and if it's like non-linear, okay, usually what a neural network could do, you can treat it as you're mapping from one space to another space. Yeah, so the idea of this feed-forward neural network is maybe to modify the embedding space in such a way that it's more suited for the current problem. So it's a sort of a mapping. So that is how you can interpret this feed-forward neural network. In fact, just to add some excitement, you know, in this multi-head attention, you have query key and value. In fact, the query key value, you actually pass it through a linear layer, or rather a feed-forward neural network first before you enter. So there's also another way that you can map your input space before you go into the multi-head attention. So yeah, feed-forward neural network in this architecture is really to represent the vector in a new dimension as necessary for the problem. Okay, so I end off here. The next time round, we will cover the more in-depth behind the self-attention block, which includes how to calculate the attention softmax using the query key and value. So this part I will spend quite a bit of time to cover. And yeah, we just end here for today.